Okay, ready to go deep.
Always.
Awesome. We're diving into Professor Ramesh Dungana's The Earth as a Planet today, specifically Chapter 8.
Great chapter.
Yeah, it is. So we want to really get a sense of Earth, not just as our home, but as this dynamic, crazy, cool planet out in space.
Right, it's more than just a rock.
Exactly. So we'll go everywhere, from that hot, fiery core to the ever-changing crust, and see how all the geology stuff affects the atmosphere, life, everything.
And we definitely can't forget those big moments in Earth's history where asteroids and comets decided to crash the party. Those literally left a mark, reshaping the planet.
Totally. We'll talk about all that and also how scientists piece together this epic history. It's like detective work on a planetary scale.
Absolutely.
So first things first, let's take a trip to the center of the Earth. Professor Dungana talks about how Earth has this layered structure. It's not just a solid ball, right?
Oh, no, not at all. Picture it like a cosmic onion.
Okay, I like where this is going.
Each layer is distinct. We live on the crust, that thin outer layer. Then there's the mantle. It's this thick layer of mostly solid rock, but it actually behaves like a really, really slow-moving liquid over long periods.
Oh, okay.
And finally, in the center, the core, and that's split into two parts. The inner core is solid, but the outer core is liquid.
Liquid. What's in that liquid core?
Mostly iron and nickel, swirling around at incredibly high temperatures. It's like a planetary dynamo. This constant motion creates electric currents, and that's what generates the Earth's magnetic field. We call that the magnetosphere.
Wait, hold on. Our planet is a giant magnet.
Basically.
That's wild. So what does that mean for us living up here on the surface?
Well, just like iron filings around a bar magnet, the magnetosphere acts like a shield.
A shield? From what?
It deflects harmful radiation from the sun. So without it, we'd be constantly bombarded with charged particles, they'd strip away our atmosphere, and Earth would end up like Mars, barren and lifeless.
So no magnetosphere, no atmosphere, no us. Got it. But how do scientists even know what's going on that far down? It's not like we can just dig a hole to the core.
It's like trying to figure out what a cake is made of by just licking the frosting. We use indirect methods. One of the main ones is studying seismic waves, those vibrations that happen after an earthquake.
Right.
By measuring how those waves travel through the Earth, how they speed up or slow down or bend, we can figure out the density and composition of the different layers.
Like a planetary ultrasound.
Exactly.
So cool. Okay, so now moving up from the core to the part we actually see, the crust. Professor Dungana describes it as ever-changing, which, the ground seems pretty solid to me.
It does, right. But over millions of years, the Earth's crust is constantly being shaped and reshaped by geological activity. Stuff like volcanic eruptions, earthquakes, even the continents moving around.
Wait, continents moving? I remember learning about that, but it's hard to imagine they move so slowly.
It's a very slow motion show, but it's pretty dramatic when you think about it.
Yeah, no kidding. And Professor Dungana talks about how all this geological activity is tied to the atmosphere and even climate change. How are those even related?
Well, think about volcanic eruptions. They release huge amounts of gases, things like carbon dioxide, into the atmosphere. Those gases can trap heat, and that affects global temperatures. And these changes over time have had a massive impact on how life has evolved. It's all interconnected.
So volcanoes are like Earth's exhales, and what they exhale changes the whole environment.
Pretty much, yeah.
Which makes me think about the atmosphere itself. I know it's not just air. Could you break down the different layers for us?
Of course. So starting from the ground up, we have the troposphere. That's where weather happens, rain, wind, all that. And most of the air we breathe is in that layer. Then above that, you have the stratosphere. The stratosphere has the ozone layer, which protects us from a lot of the harmful ultraviolet radiation from the sun.
Right. So the stratosphere is where we get a tan, but also where we're protected from getting fried by the sun.
Exactly. Above that is the mesosphere. It's much colder, and that's where most meteors burn up.
Like a cosmic shooting gallery. What's after that?
Lastly, we have the thermosphere. It's the outermost layer, where the atmosphere gradually fades into space. That's where you get the aurora borealis, those beautiful northern lights.
Wow. So it's this multi-layered life support system, protecting us, regulating temperature, letting us breathe. Amazing. But earlier you said that life on Earth actually helped shape the atmosphere. How does that work?
Oh yeah, that's a really important point. You see, the early Earth's atmosphere was completely different from what we have today. Much hotter and with no free oxygen.
Really? No oxygen.
As we know it, no trees, no animals. And it wasn't until these tiny organisms called cyanobacteria showed up that things started to change.
Cyanobacteria. What are those?
They were like the pioneers of photosynthesis, using sunlight to make energy, and they released oxygen as a byproduct. Basically, these microscopic life forms terraformed the planet.
They terraform the whole planet.
Over millions of years, they pumped out oxygen and completely changed the atmospheric composition.
So tiny organisms transform the entire planet. That's incredible. But how do we even know all this about the early Earth?
That's where things get really interesting. We'll get into all that in the next part of our deep dive. We'll explore how scientists piece together this ancient history.
Can't wait. This is blowing my mind already. Okay, we're back. And man, my mind is still spinning from that last part.
It's crazy to think about those tiny organisms changing the whole planet, isn't it?
Absolutely. But I'm still stuck on how scientists actually figure out all this ancient history. Like, it's not like we can just hop in a time machine.
I wish, right?
Yeah.
But we do have some pretty amazing ways to reconstruct the past.
Okay, tell me more.
Well, one method is radiometric dating. Remember those radioactive isotopes we talked about earlier?
Yeah, they decay over time, right?
Exactly. They act like a clock, but instead of seconds, they're measuring millions or even billions of years.
A billion-year clock, that's wild. So by analyzing how much those isotopes have decayed in rocks and minerals, scientists can figure out how old they are.
Precisely. It's one of the most reliable ways we have to put a date on events in Earth's history.
That's so cool. But rocks aren't the only clues, right?
Definitely not. There's also paleomagnetism.
Paleomagnetism. That sounds complicated.
It's actually pretty simple. The idea is that when rocks form, they lock in the direction of Earth's magnetic field at that time.
Oh, okay.
So by studying those ancient magnetic records, we can reconstruct how continents have moved over millions of years.
So it's like a compass frozen in time.
You got it. It helps us understand how the Earth's surface has changed over vast stretches of time.
This is incredible. And what about the climate? How do scientists know what the climate was like millions of years ago?
That's where paleoclimatology comes in. It's basically like a weather report from the past.
Okay, I like it.
Scientists study things like ice cores, tree rings, and sediment layers.
Ice cores. What can those tell us?
Ice cores are amazing. They trap tiny bubbles of ancient air, and by analyzing those bubbles, scientists can learn about the atmospheric composition from long ago.
So they're like little time capsules.
Exactly. And tree rings can tell us about rainfall patterns and temperature changes over the life of a tree. And sediment layers, they hold all sorts of clues about past environments.
It's like reading a history book written in ice and rock.
That's a great way to put it.
We've been talking a lot about how geological activity shapes the atmosphere. But what about the other way around? Can changes in the atmosphere actually influence geological processes?
You're thinking like a true scientist, and the answer is yes. Remember how we talked about volcanoes releasing carbon dioxide into the atmosphere? Well, if there's a big increase in carbon dioxide in the atmosphere, it can actually speed up the weathering of rocks.
Wait, so the air can break down rocks? How does that work?
Carbon dioxide in the air reacts with rainwater to form a weak acid called carbonic acid. And this acid rain, it can dissolve certain types of rocks, like limestone. And as rocks weather, they actually absorb some of that carbon dioxide from the atmosphere, which helps regulate the climate over long periods.
So it's like a feedback loop. The atmosphere influences the rocks, and the rocks influence the atmosphere. It's all connected.
Exactly. And that connection highlights how dynamic and interconnected our planet truly is. It's a delicate balance.
Speaking of connections, we've been so focused on Earth itself, but we're part of a much bigger system, right?
What about the influence of other celestial bodies on Earth's history?
Absolutely. We can't forget about our cosmic neighbors. We've touched on asteroid impacts, but what about the moon? It plays a crucial role, too.
I know it causes tides, but what else does it do?
Well, for one, the moon's gravity actually helps stabilize Earth's axial tilt, which is what gives us seasons.
Oh, wow.
Without the moon, our planet would wobble much more dramatically, and that would cause extreme climate swings that would make life as we know it pretty much impossible. So the moon is like a silent guardian, keeping our planet steady and our climate in check.
Yeah.
That's amazing. But didn't you also say that the moon is actually slowing down Earth's rotation?
That's right. The moon's gravitational pull is very gradually slowing down Earth's spin.
So what will days be like in the future?
Well, millions of years from now, days will be longer, but we're talking about a tiny fraction of a second per century.
So nothing we'll notice in our lifetime. That's a relief. I kind of like our 24-hour cycle.
It's a good system, but it's a good reminder that even seemingly constant things like the length of a day can change over cosmic timescales.
It really puts things into perspective. This deep dive has been incredible. We've gone from Earth's fiery core to the influence of the moon. We've talked about the ever-changing crust and the delicate dance between the atmosphere and life itself. What's next on our journey?
Well, we've explored Earth's own story, but to truly understand its place in the universe, we need to look outward. In our final segment, we'll explore how scientists study other celestial bodies, from planets to comets, to gain insights into Earth's own unique history and evolution. It's like comparing notes with our cosmic neighbors.
I can't wait to see what we can learn from them. Let's dive into the final chapter of our exploration. All right, we're back, ready for the final part of our deep dive into the Earth as a planet.
Absolutely. Let's do it.
Awesome. So we've gone from Earth's core to the moon's influence. Now we're zooming out even further, right?
That's right. We're going to see how understanding other celestial bodies, other planets, moons, comets, can actually help us understand Earth's own story even better.
It's like looking at a family photo album. You can see the shared features and then the things that make each person unique.
I love that analogy. It's so true. By studying these other worlds, we get a fresh perspective on what makes Earth, well, Earth.
So how do we even study things that are so far away? We can't exactly hop in a spaceship and go take a look, right?
Not yet, anyway. But we do have some pretty incredible tools. Telescopes, for example, let us observe these objects from a distance. We can learn about their composition, their atmospheres, what their surfaces look like.
Probably telescopes.
And then we have space probes and landers that we've sent to places like Mars and Venus. We even landed a probe on a comet. That's getting up close and personal.
Wow, that's amazing. It's like we're sending scouts out to explore for us. Professor Dungana talks about this idea of comparative planetology. What is that exactly?
Comparative planetology is basically just what it sounds like. We study planets by comparing them to each other, looking at the similarities and differences to try and figure out what processes led to their formation and how they evolved over time.
Okay, so why is Mars a dry, dusty desert, but Earth is teeming with life?
Exactly. Or why does Venus have this incredibly thick, toxic atmosphere? Comparative planetology helps us answer those questions.
So each planet is like a piece of a giant cosmic puzzle. And by studying them all together, we get a better picture of how Earth came to be the way it is and why it's so special.
Absolutely. And it's not just about looking back in time. Comparative planetology also helps us understand what might happen to Earth in the future. Like, by studying the runaway greenhouse effect on Venus, we can get a better idea of what might happen if climate change gets out of control here on Earth.
Okay, so it's not just about curiosity, it's about our own future too. Fascinating. Professor Dungana also talks about how scientists date the surfaces of other planets. We talked about radiometric dating for rocks on Earth, but how do you date a surface on, say, Mars?
Well, one of the main ways is by counting craters.
Counting craters.
Yeah. Over time, planets get hit with asteroids and comets, leaving behind craters. The more craters there are in a certain area, the older that surface probably is.
Oh, so a heavily cratered planet has just been around long enough to get hit more times.
Exactly. And by comparing crater densities, we can even get a sense of the relative ages of different planets, and even the history of bombardments in the solar system.
Okay, so craters are like historical records. I never thought of it that way. But let's talk about a different kind of celestial visitor. Comets. What role have those icy wanderers played in Earth's story?
Comets are thought to have delivered a lot of the water we have on Earth and other essential ingredients early on in its history.
Hold on, so those dirty snowballs from space might be the reason we have oceans and life itself.
It's a leading theory, and it really highlights how interconnected everything is, from the smallest atom to the vastness of space. Earth's story is really a cosmic story, woven together with the lives and deaths of stars, the journeys of comets, the collisions of asteroids.
Wow, that's pretty mind-blowing. So what's the big takeaway from all this? We've traveled from the Earth's core to the icy realms of comets, looked at other planets for comparison, and learned about all the amazing things happening on our own planet.
The biggest takeaway for me is that Earth is not just a rock. It's this dynamic, living, breathing system, constantly changing and evolving, shaped by both forces within and events happening out in space.
I think this deep dive has really changed how I view Earth, that's for sure.
Me too.
Thanks for joining us on this incredible journey. And to everyone listening, keep looking up, keep wondering, and keep exploring. Who knows what other amazing secrets are out there waiting to be discovered?